And we're going to answer some BFF questions using your note cards as assistants. Okay? So number 19, we're starting with the four functions that are odd. Now, we talked about what odd meant. Who remembers what odd means in terms of functions? It means symmetry about the origin, which in kind of like simplistic terms means that whatever is happening in quadrant 1, for example, is also happening in quadrant 3, across the origin. If you threw a ball across the origin. So apparently there are 4 of these, and I have drawn one of them. Which function is this?
Identity.
That's the identity. The identity is odd. All right, look at your cards, look at your pictures. Do you see any others where the picture in quadrant 1 is kind of flipped over and duplicated in quadrant 3?
I just are we doing just like the name of the function, or are we doing the ones that are right here, like number 1, number 2?
No, we are on page 113,
Yeah,
doing number 19.
yeah, but it says like to use like the displays.
Oh,
I'm asking if we're just doing
we're
that.
doing the BFFs. Yeah, we're just
Okay.
doing our BFFs. Yeah, our BFFs. Good question.
Greatest integer.
Oh, Warren, I hate that function. That is a little bit tricky because the answer is no, it's not I, and here's why. If I were to take this picture and flip it across the origin, this dot would be open and that dot would be closed. The dots need to switch. You're flipping at 180 degrees. So when you flip at 180 degrees, it reverses those. So very good guess, sort of makes sense, but it's not. Okay, Braden? Cubing function, absolutely. Because think about when you draw a cubing function. In quadrant 1, you have this shape, and in quadrant 3, you have the same shape flipped 180 degrees. Perfect. Katie?
The reciprocal function?
Absolutely. The reciprocal function is odd because what you draw in quadrant 1 is exactly what you draw in quadrant 3. There's supposedly one more. Can you think of what it is, Dan?
Is it solid?
Yes, it is. Very good. That's the tricky one. But Van says, okay, if I look at just the first part of the sine curve, isn't that duplicated in quadrant 3? It is. Sine is odd. Very, very good. We may not do all these, but let's do a couple more. The 6 functions that are increasing on their entire domain. All right? So the 6 functions that are increasing on their entire domain. Now, what that means is, when you sat down to draw the picture on your note card, when you drew it, your hand was only going up. Only going up. So, it's not the absolute value, because when you draw the absolute value, your hand goes down, and then it goes up. So that's not 1. I want a picture that my hand only goes up. Would the identity be 1?
Yep.
Right, what else? You're going up only when you draw it. Square root. Remember the square root function has a dot right here and goes out like that. Perfect. What else?
Exponential.
Exponential. The exponential. That does not look right to me, but we'll hope it's right. So the exponential has an asymptote here, and goes up when you draw it. Beautiful. Okay?
Logarithmic.
Logarithmic, absolutely. The logarithmic function, remember, only goes up. Two more that only go up. Logistic only goes up. Do you remember what that one looks like, guys? The logistic has the asymptote at top and bottom, and then squiggles up like that. Only goes up. We're talking about drawing left to right. Only goes up. One more. I'm surprised you don't have it yet. I'm easy cubing. The cubing right here, cubing goes up. Only up. So we say these guys are increasing on their entire domain. That means the entire picture is going up.
So would greatest integer not be one because you like lived up your pencil?
No, this isn't even a continuity. Greatest integer isn't one because, is my pencil going up when I'm drawing that bar?
Okay.
No.
Okay.
Have to be going up the entire time. All right, three functions is 21. The three functions that are decreasing on the interval from negative infinity to 0. So there are three functions, apparently, that when you draw them over here on this side, negative infinity to 0, just this side of the picture, they go down. When you think of a picture that goes down over here, Robbie? Absolute value. Doesn't it go down on this side, guys? All right, two more.
Reciprocal.
Reciprocal. The reciprocal function looks like this. Isn't that going down, guys? Perfect. All right, one more goes down. Huh? Squaring. Squaring is just like the absolute value, but it's a u instead of a v, so just squaring. So these six were increasing on their entire domain. They're always increasing. These guys, at least this one and this one, are decreasing for part of the time and then increasing for the rest of the time. Would you agree? All right. One more. Number 23. The three functions with no zeros. Okay, what are zeros again? X-intercepts. I heard someone say it. Awesome. Zeros are X-intercepts. You need to know that word. So there are three functions that do not touch the x-axis.
Exponential.
The exponential doesn't touch the x-axis. Would you agree with that? Katie? Logistic does not touch the x-axis. Good. And the last one, Robbie?
Reciprocal.
Reciprocal does not touch the x-axis. Very good. Now, guys, answering these questions is not too bad when you have your cards right in front of you. But we gotta get to the point where we can have this conversation without the cards. So we're working on that, right? What did I give you till when to have it all figured out?
3 weeks from today.
Whenever our next class is,
Last time.
right? So we're gonna be studying these a little bit, so that we can memorize the shape, the name, and the equation, and we should be good to go. All right, let me see if there's any more that I think were really interesting. No. All right, let's get our calculators out. Let's do a little sketching on our calculator, and we're gonna talk about domain and range. Now, this first problem, before we type it into our calculator, I think you should be able to sketch that without a calculator. We're gonna do it on the calculator too, but what do you think it looks like now, without a calculator, just sketching it? What shape do you think it's going to have? A parabola. What does this do to the parabola? Down 5, right? This is your BFF right there. We moved it down 5. So when I sketch this on my calculator, I better see a picture that looks like that. All right, let's go ahead. No big deal, you all know how to type this in. Did you get which dots you were going to get? Okay, tell me about domain and range. You don't need a calculator to do this. You can look at this and tell me the domain and range. What's my domain? All reals. And for those of you that are like, ooh, how do we know that? Remember, there are two things that screw up your domain, right? Denominators and radicals. If you have a polynomial function, like this, no domain, no square root, and no denominator, then it's all real numbers. Now, what about range? -5 to infinity. That is exactly right. Is everybody okay with that? It's pretty easy. All right, let's try number 2, or B, first without a calculator. Okay, so let's try it first without a calculator. So tell me what we've got going on here. What shape is this going to be? It's going to be a logarithm function, right? Right? So we know that the normal picture has an asymptote at 0, an intercept at 1, and it shoots out like that. That would be the normal picture. Now in a minute, I'm going to put it in my calculator, but right now, what does that do? Moves it, someone said it, left 6. So this asymptote, which is originally at 0, is now going to be at -6. And this intercept, which was originally at 1, is now going to be at -5. So it's exactly the same shape, just moved back. All right, let's graph it and see if we get something like it. You won't see the asymptote. Well, I don't know. On those new calculators, you see all kinds of stuff. I'm not going to see the asymptote. I know that. Now, this is where it really helps to have a working understanding of what these things look like. On my calculator, I don't see this, and I see something like this. Anybody have an old one like me, and that's what you see? So it looks like maybe it starts right there, but it doesn't. It actually keeps going down, 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 down forever and ever. I would not know that from my calculator, but I know it because I know what that shape is. Now, on the new ones, who's got a new one? Did you get a big picture on the new one?
Yeah, it's just been,
It still stops?
yeah.
Oh crap, it does. Okay, yeah. So, now we gotta know. We gotta know what it looks like because our calculator lets us down. What's the domain and range this time? Domain? Whoa, 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 whoa. I don't think it's all reals. This is not a polynomial. This is a weird function that has restrictions right from the beginning. -6 to infinity. That's your domain. Because there is an asymptote right here at -6, and aren't we getting closer and closer to it as we go down? Don't say -5 because it doesn't start at -5. It actually starts just a hair to the right of -6. So that's your domain. Now your range is all real numbers because this picture goes all the way down and eventually all the way up. It arcs out, but it keeps getting bigger and bigger. Okay? So we're not going to rely on our calculator too much. All right, next, we're going to sketch it by hand first. And then we'll get our calculator out and see what the calculator says. All right. You know what that looks like, right? That's your reciprocal. I'm going to go ahead and sketch your asymptote at 0 and 0. And then a curve in here like this. Now, what have we done? We've added a 3, which does what to the picture? Up 3. Up 3. Remember, when you put the added number or subtracted number inside the problem with the x, like in a parentheses, that moves you sideways. But when you tack it on the end, so I just took my BFF and stuck a +3 on the end, that moves you up and down. So we're going to take that picture right there, and we're going to move it straight up 3. Now, will moving it up 3 affect the vertical asymptote? No, so I'm not going to read that there. Will moving it up 3, the whole picture, moving it up 3 affect the horizontal asymptote?
Yes.
Yeah, it's going up to 3. Now, the curves are staying exactly the same. But it has been shifted up 3 units. All right, let's graph it on our calculator. See what we see. 1 divided by x plus 3. Do you see something that looks like this? Tell me domain and range. What's my domain and range for the sky? Ready?
Oh, is your domain negative infinity to 0, union 0, negative 0,
Perfect.
infinity?
Perfect. That is exactly right. Does anybody need to ask him what he means by that? He's got it. We take out 0, right? So everything to the left is 0, everything to the right is 0. What about my range? 4, or Ellen?
Negative infinity to 3, union 3.
Remember, I know you know this, the infinities are always open. Asymptotes have to be open too, because you don't touch them. So anytime you're using an asymptote as one of your endpoints, it's got to be open. Okay? All right. 2 more, and then we're going to do a piecewise function. All right, so let's graph the next one. We'll skip the by hand part. I know you could do this one. What shape will it be? Be a V, let's graph it on our calculator. Did we talk about how to get absolute value?
Yeah.
Math,
2.
number, absolute value, x minus 4. Did you get a V shape? Is it moved the way you anticipated it moving? 4 units to the right? That's different, gang. That's different than this. Right? Okay, domain and range for this guy. Domain? Or real? No restrictions on the domain? How about range? 0 to infinity. Isn't 0 the lowest point? And it is included. It's not an asymptote. It is included. And we're going up from there. Now my least favorite. All right, know where you got absolute value? You know where you got it? Okay, you're gonna get INT the same place, just down the list a little bit. And we're doing x divided by 2. Now, I wanna see a new calculator.
Present election at this time. Any senior who is going on senior retreat, we ask that you now start making your way to the SLC. Again, all seniors going on retreat,
So I
please
sent
go
you an
to the
email, Sharon, so
SLC.
you know
Thank
what
you.
you need to do, okay? All right, so if you have a new calculator, do you actually see the steps?
Yeah.
Isn't that awesome? If you have an old one like me, like the new ones actually show this. Mine does this because my calculator can't lift its pencil. So it goes over and then it comes up, and then it goes over and then it comes up. So I see the steps, but I don't have the gaps between them. I do want you to make one quick observation though about the length of those steps. Yeah, isn't that interesting? When it was x divided by 2, we actually didn't divide the length, we actually doubled it. So if you think back, Allie, you'll remember doing some of that before.
Yeah.
With that same idea. I always think about it like this, kids. When we have x minus 2 in parentheses, when I see a minus, I think left, but that isn't what happens, right? It actually goes to the right. When you put something to an x, it does the opposite of what you think. So when we put a 1/2 x into our problem, it actually doubled. It didn't have it, it doubled it. It's interesting, isn't it? All right, now we're gonna do a piecewise function. We are not gonna be deterred. We're gonna get this done. So number 4a, we're gonna graph it right now. 4a.
What would be the domain on that?
The domain for that is actually all real numbers.
Oh, really?
The range is going to be integer values, and it's weird, let's not worry about it.
Oh, okay.
Yeah. I'm lucky, I'm the teacher, so if I don't like something, we kind of just lost it. All right. All right, this is called a piecewise function. And it's called piecewise because it's literally written in pieces. And therefore, it will be graphed in pieces. Okay? So here we go. I have a little bit different way of doing this than other people. I never care how you do it. It's on let me show you how I do it, it helps me keep track of everything, you have your one. The break in this equation, or in this function, the break comes at 0. This tells me where I split it into pieces. So I like to put a little squiggly line, which is not part of the graph, so I do it really lightly. And I put a little squiggly line at wherever my graph is broken. In this case, it's broken at 0. Now, I'm going to graph this. Well, what is that? Y equals X. Y equals X. What is that? That's the identity of the linear function. Sketch it in. There it is. Notice that my line, which is just my BFF, easy, it crosses my squiggly line. So I make a big dot there where it crosses. That dot will actually be colored in because of the or equal to on the 0. Now, as soon as you put that dot on there, you have split your line into the left piece and the right piece. In a piecewise function, you only want one piece. So look up here. This tells me which piece I want. I want the piece to the left. So I'm going to take my eraser and I'm going to erase the piece to the right. There is the first piece of this function. Now, what shape is the second piece of the function? It is a parabola. And it also starts at the origin. So up it goes. There's my parabola. Now, usually the pieces don't have that point in common. So normally I would have another dot somewhere. But here I have a dot here. Technically it's open, but guess what? I already colored it in, right? Which piece of my parabola do I want? The right, so I'll erase the left, and there is my piecewise function. This squiggly line is really not part of the picture. I don't care if you leave it in, you can absolutely leave it in if you want, but it isn't really part of the picture.
If we're writing that, do you want to make the circle big? Like we
Yeah,
kinda did?
I think that makes it easier, I don't care, I need to be able to tell if it's open or closed.
Okay.
The circle's open or closed based off of the equation on top?
Yep.
So always open?
Always,
Okay.
always. And this is where you put your squiggly line. It won't always be on an axis. Look at the next problem. Well, no, go down to the bottom. On the bottom problem, there's going to be two squigglies. One of them will be at 0, and one of them will be at 1, because those are the x's that break up the picture. Okay?
On the second piecewise up there, if that was like x is greater than like 2, there would be a dot on 2 and that would be open, right?
Yep. Yep. So we're out of time today, but we will definitely finish this up next time. And next time we will also finish this section, so you can actually start working on the homework now maybe. It'll be due, when did I say